Thanks very much, Greg. I read I'm not a football fan, but I read somewhere that during the World Cup, the Brazilian police were issued with helmets, which produced a heads-up display when they were approaching known troublemakers. So it was facial recognition software, would identify it and say, this person is from so-and-so, and it's caused trouble in the past, and blah, blah, blah. If they can do that, why can't they produce it in glasses like these, so that when you're faced in the supermarket by a woman who you haven't a bloody clue who it is, says, this is your mother's neighbor at the back. The last time you spot, that would be really useful. That's technology that's actually worthwhile to my mind. And how mad would you be if your alarm clock could actually make up its own mind to wake you earlier in the mornings? It would last about 20 minutes in our house, if that. Our next speaker, Chris Bishop, is Chief Research Scientist for Microsoft UK, and building on what Greg's just done, Chris is going to look slightly further out. So, Chris.
In 1854, there was a bad outbreak of cholera in the Soho district of London. Now, at the time, people thought that cholera was caused by breathing some sort of bad air. But there was a rival theory. It was the theory that cholera was somehow contracted by drinking contaminated water. And so somebody who was a supporter of that theory, Dr. John Snow, did a very simple thing. He took a map of Soho and he plotted the cases of cholera. So each dot represents a person who's contracted cholera in 1854. And he also plotted the positions of the various water pumps in that part of London. And he noticed a rather obvious thing, which is that there's a big cluster of cholera cases around the Broad Street pump. So he persuaded the authorities to remove the handle from the pump so that people had to use other water pumps, and the cholera subsided in that part of London. So in the process, he undoubtedly saved several lives. He also invented the critically important field of epidemiology. Now, in a sense, he was one of the early users of what today we might call big data. It wasn't very big in those days, but of course, the big transformation that's happened since 1854 is the internet and the rise of digital technology. And for the last 50 years or so, the digital revolution has been driven by one simple fact, Moore's law. The Moore's law of transistors, the fact that the number of transistors that we can pack onto a square centimeter of silicon has been doubling about every 18 months. What we're seeing now is a second kind of Moore's law emerging. It's a Moore's law of data. The amount of data in the world is growing exponentially, and the doubling time seems to be about the same. About every 18 months, the amount of data stored in the world is doubling. Now, you're probably all fairly sick of hearing the term big data. We've had lots of hype. We've heard one example, the data is the new oil. But new technologies go through these three phases. There's the phase of hype, the phase of disillusionment, and then finally reality and perception finally catch up. And it's a property of exponential growth that from the point of view of a casual observer, it seems as if nothing is happening, and suddenly explodes into being. And the same thing will happen with big data, that behind the scenes there's exponential growth, and one day we'll find it's all around us, it's influencing every aspect of our lives. So in spite of the hype, I do believe this will be transformational. So, you've got data. What can you do with it? So I'm going to talk about 4 things we can do with data, a kind of hierarchy, if you like. So the simplest thing that you could do with data, and it's very useful and very powerful, is to visualize the data. So for example, you could just plot the location of all the crimes in a city, and that would help you to decide which part of the city you should avoid buying a house, and in which part of the city you might wish to buy a house. So just visualizing the data is already very useful because the human brain is very good at interpreting data when it's visualized appropriately. So that's the simplest thing we can do with data. But there's a lot more we can do. So the next sort of level of sophistication is to compute functions of the data. Just algorithmically take the data, process it, and output quantities which are simply functions of the data. We call those functions statistics, and those statistics tell us more about the data than we can get just from visualization. So for instance, the average height of the population would be a statistic that we could measure from the data, or the day of the year on which the highest number of crimes are committed, that would be another statistic. So visualization, statistics, those are the kinds of things that people often mean today when they talk about data, collecting data, using data, fusing data from multiple sources, computing statistics on that data. But there's a lot more that we can do with data. and these techniques are going to become increasingly prevalent in the years ahead. So the next sort of level up is to compute much more complex functions of the data. This is the field of machine learning. So many techniques, not all, but many techniques in machine learning seek to create what you might call a prediction engine. So a prediction engine is something which takes a quantity that you can measure and outputs or predicts a quantity that you can't measure directly but that you'd like to know. And I'm going to show you an example of that in a moment. But there's even more we can do than just build prediction engines, and really this is the sort of the main theme of this talk. It's something which is very much at the cutting edge of research. I'm from Microsoft Research, I'm a research scientist, and this is something which is highly active at the moment and which I hope and I believe will have an increasingly profound impact over the next 5 or 10 years. And that's the idea of building rich probabilistic models of the data. And again, I'll show you an example of that a bit later. Let me first of all just say a little bit about machine learning, because many of you may have heard of this, you may not all have heard of it, you may not all know what it is. So I'm just going to show you one example of machine learning. It's something that was developed a few years ago by my research group in Microsoft Research in Cambridge, and it's a thing called the Kinect. And so this is a little video of one of my interns playing a game on the Xbox. This is the Xbox console, and sitting on top of the Xbox is the Kinect sensor. And you'll notice that as she moves around, this little avatar is tracking her arms, legs, her entire body is being tracked in real time as she moves around. And then that tracked motion is being used to control the computer game. And as Greg commented, people don't want to put on fancy gloves like in Minority Report or wear bits of special suits or anything like that. So this is all done without having to put on any devices or having to wear any special clothes. You simply walk in front of the sensor and it starts tracking your body in real time. So how does this work? Well, in essence, there is an infrared emitter that's putting out a laser pattern into the environment, and then a short distance away is an infrared camera, and that displacement through a technique called parallax allows the camera to see depth, to see in 3 dimensions. And the newer version doesn't use quite the same techniques. It uses time of flight, but the end result is the same. It's a camera which sees the world not in intensity of light or in red, green, blue, but in depth. This is a depth camera. So this is what the camera sees. This is just a person moving around in front of the camera. And here the grayscale represents distance from the camera. So as they come closer to the camera, the pixels become darker. And as they move away, the pixels become lighter. So this camera is seeing the world in 3 dimensions. And that makes it much easier, still difficult, but much less difficult to track motion compared to using a standard red, green, blue webcam. So that's what the sensor sees, but what we want is the 3-dimensional location of all the body joints, so we have the skeleton in 3D. So how are we going to do that? Well, we use a technique called machine learning. So imagine each frame of that video, 30 frames a second, take each frame of that video, each pixel is a depth, it's a distance from the camera. So that's the thing that we measure. What we'd like to have is a corresponding frame in which each pixel is labeled either as background or it's labeled according to which part of the human body it belongs to. So we define 31 different body parts, the left elbow, the right knee, and so on. And the thing we'd like to happen in real time for every pixel in every frame is to have a label saying which part of the body that corresponds to. And we do this by building a function, a mathematical function, which takes the thing we measure as input and produces the thing we want to know as output. And this function has thousands or millions, depending on the application, of adjustable knobs, parameters, quantities that can be tuned. But we don't set this by hand. We don't program this by hand. Instead, we program this system to learn from data, and then we show it lots of data. In fact, we show it 1 million examples of different people in different poses, together with the labeled ground truth. So for 1 million images, we use a motion capture suite, a Hollywood-style motion capture suite, where somebody wears ping-pong balls on a special suit. They're viewed by multiple cameras in real time, tens or hundreds of thousands of dollars for this very sophisticated room, which can track the person in 3 dimensions in real time and provide us the ground truth to go with the sensor data. So this is the actual data that was used to train version 1 of Kinect. It's 1 million body poses, each one colored here according to the different body parts. And these have actually been arranged spatially on the screen in a way that will become apparent in a moment. So a million's actually quite a big number. We think of it as sort of a small number these days, but that's what a million body positions looks like. So that's the training data that's used to train that function. You may have heard of deep neural networks. They're very popular at the moment. For efficiency reasons, we use a system which is a very fast system called decision forests. There are many, many other techniques that have been developed. And so once all the parameters have been tuned, it can take a new depth image and output the body part labels for every pixel on every frame in real time. And so this is the result of that trained system. So this is what the sensor sees, this depth video sequence. And then our machine learning system, running in real time, I should say, by the way, that to tune those parameters, that training or learning phase is very slow. That can take days or weeks on big clusters of computers. So it's a very slow, compute-intensive process. But once the system is trained, it can make new predictions very, very quickly. And so these are the real-time predictions in which each pixel has been labeled according to which body part it represents. If you like, that's the hard part. There's then a little bit of post-processing to be done. Once you've got the labels of all the pixels, you can do a little bit of clustering and extract, in a robust way, the joint locations. Because if you know the locations of all the joints of the body, then you know what the skeleton is doing in 3 dimensions. And because this is a depth video, because we're tracking the skeleton in 3D, we can view this from the front or from the side or from above. And so that's Connect. That's how Connect works. So that's an example of machine learning. And there are thousands of examples. You will have used machine learning several times already today, filtering email, making recommendations, doing all sorts of things. Machine learning is very widespread. It's becoming increasingly prevalent. And machine learning, of course, is dependent on the idea that instead of programming a computer to solve a problem, we train the computer by using data. And so if we're in a world of exponentially increasing data, and if that data contains useful information, then we can expect to see more and more applications of machine learning. I want to make a comment on this phrase big data, though, because it can be misleading. So if you ask somebody what they mean by big data, as opposed to just sort of data, you might get an answer that refers to the amount of data, if you like. It might refer to how many terabytes or petabytes of data you have to deal with. Perhaps the fact that even storing the data or processing the data or moving the data from one place to another is non-trivial. It's data at scale. But there are 2 completely different notions of the size of a data set. And it's incredibly important to distinguish between these 2 concepts of the size of a data set. So there's the computational size, and then there's the statistical size. And the statistical size of the data set has to do with the information that it contains. And that distinction between data and information is so important that I'm going to discuss that in more detail in a moment. But let me just give you 2 sort of extreme examples, 2 kind of corner cases to explain the difference between the computational size of a data set and the statistical size of the data set. So here are 2 problems for which we might apply something like machine learning. So imagine we've got a lump of material, and we apply a voltage across that block of material, and we measure the electrical current that flows through it. And we'll apply different voltages, and for each voltage we'll measure the current, and we get some data. And we've got 7 data points, 7 measurements. And we'd like to use that to train some sort of prediction engine. We'd like to predict the current that will flow through this for some new voltage where we haven't yet made a measurement. So that's the goal of our prediction engine. Now, imagine that some kind physicist has told us about this thing called Ohm's law. And this kind of physicist has told us that there's a linear relationship, in fact a proportional relationship between current and voltage to a good approximation for this particular material. Then we know that the relationship between current and voltage is described by a straight line. Now a straight line is governed by just 2 parameters. And in fact, if it goes to the origin, it's governed by just 1 parameter. So even 1 data point would give you a good idea of what that line looks like. Now, the data, of course, are real measurements in the real world, and they're sort of noisy. So you can say they don't all sit on a line. They're sort of jiggled about a little bit. So if you have several measurements, you can kind of average out the noise. You can make better predictions by having several measurements. So with 7 measurements, we can pin down the slope of that line really quite accurately. So here's an example where we've got a data set that is 7 pairs of floating point numbers, 14 numbers. Computationally, it's trivial. It's a minuscule data set from a computational point of view, but statistically, it's huge. By that, I mean the following. If I gave you another 1,000,000 measurements of current versus voltage, you would be able to make slightly better predictions. But nearly all of the information is in the first few data points. So it's a computationally tiny data set, but statistically it's huge. Now, in the world of the internet and web and so on, we have to deal with data sets which are often computationally large, but they may not be statistically large. So here's sort of a hypothetical example of that. Imagine I've got images, and each image just contains an object. So it might contain an aeroplane or a bicycle or so on. I want to build a prediction engine which can take that image and just tell me the category of object in that image. Now, each image might have 1,000,000 pixels. Each pixel has sort of red, green, blue intensities. And I might have lots of examples of aeroplanes, lots of examples of bicycles, and so on. Let's suppose I've got 1,000,000 examples of each. Okay, so each image has 1,000,000 pixels, and I've got 1,000,000 examples of aeroplanes, 1,000,000 examples of bicycles, and so on. I'm now dealing with a data set which computationally is becoming non-trivial. It's becoming big data in the sense of just the amount of ones and zeros that I have to store and process. But does that characterize, do the 1,000,000 images of an aeroplane characterize what it is to be an aeroplane? Well, let's think about it. First of all, the aeroplane could be anywhere in the image. If I move the aeroplane, it's still an aeroplane, but all those pixel numbers change in complicated nonlinear ways. If I rotate the aeroplane in 3 dimensions, those pixels change. If it gets nearer or further away, they change. If I change its color, if I change the lighting, if I change the reflectance of the surfaces around it, the pixels change. It's still an aeroplane. And furthermore, I can take any combination of translations, rotations, lighting changes, color changes, and so on in combination. So the number of combinations is growing exponentially. So in other words, if you considered all of imagine a space, every point in the space is every possible 1,000,000 pixel image is represented by a point in some space. That space is so vast that 1,000,000 examples will be extremely sparse in that space. In other words, all the images that you would agree constitute images of aeroplanes, the number of such images is vast compared to 1,000,000. Right? Vast compared to the number of electrons in the universe, in fact. So here's an example of a data set which is computationally large but statistically tiny. Now, for the experts in the audience, you'll point out, of course, that that's not quite how we do computer vision. We're a little bit smarter than that, and we take out these invariances so we don't have to deal with them. And then with 1,000,000 examples, we can actually represent aeroplanes. So it's a little bit of a hypothetical example. But in reality, we're often having to deal with that. We're dealing with very large data sets, and yet they're statistically sparse. So that's important. I'll explain why it's important in a moment. So if we have data that is, if you like, sparse, we have to deal with uncertainty. In the case of Ohm's law, once we've seen enough data points, we're pretty certain of the resistance of that material. But if we're dealing with data which is computationally large but statistically thin, then we need to deal with uncertainty. And it's everywhere. So if I want to recommend a film, a movie for you to watch, I'm uncertain. Even if I know a lot about you, I can have a pretty good guess as to which movie you might like, but I can't be absolutely sure. Which word did the user write? Again, we can build pretty good word, that is, electronic ink handwriting recognition systems, but especially if it's scrawly handwriting like mine, the computer will be uncertain about exactly what I meant. Was that an O? Was that a 0? We're not quite sure. Speech recognition systems, notorious for not being 100% accurate the whole time. There's uncertainty about what the user said. Which web page is the user trying to find? If we're doing web search, which link will the user click on? Very important for online advertising. What kind of product does the user wish to buy? Which gesture is the user making? If we're doing gesture control in some natural user interface. Many, many others. In fact, virtually every application that you can think of is going to involve some degree of uncertainty. So uncertainty is becoming central to computer science. That's quite interesting because Computer science has its foundations in the work of people like Boole and Turing and von Neumann, who thought of computation as logic. Everything was deterministic. It was 1 or 0. The transistor or the valve was on or it was off. There was no uncertainty. And the engineers worked really, really hard when they're designing chips to make sure those transistors are unambiguously either on or off. So logic is at the very heart of computing. And yet today, we're asking computers to deal with uncertainty. We want to deal with that uncertainty, not in an ad hoc way, but in a principled and optimal way. So we need a framework for dealing with uncertainty. And I'm going to introduce that framework with a little demo. And this demo is to do with recommending movies. So this particular demo is just a small-scale demo that's built for purposes such as this, for giving talks. The technology behind it, though, powers large-scale recommendation engines. So what we've got here is a selection of movies, and each of these movies has been rated as either I like it or I don't like it by a few tens of thousands of people. So we've got a few 100,000 recommendations. So imagine a sort of matrix of people and movies. We've got sparse entries in that table where a person liked a movie, another person didn't like some other movie. Now, in reality, we know stuff about the movies. We know that it's a romantic comedy or an action-adventure, and we know something about the person, their age, their gender, other factors that might be relevant. For this demo, though, we're just going to ignore all that. Just for the purpose of the demo, pretend we don't know any of that. So in this demo, all we have is a bunch of people, 1, 2, 3, 4, 5, and a bunch of movies, A, B, C, D, E, and all we know is that person 3 liked movie C, and person 15 didn't like movie H. Okay, that's all the data we have. That data has already been absorbed into a probabilistic model. That was the sort of fourth level of this hierarchy of things that we can do with big data. So behind the scenes, already what's happened ahead of time is that that data has been munched into this probabilistic model. And now we have a system which understands the sort of patterns of likes and dislikes in this population of people. But it's now going to make recommendations for me. And these are going to be personalized recommendations. Now, it doesn't have any ratings for me at the moment, and because we're not going to allow it to know about types of movie or the properties of an individual, all it could do is just recommend the most popular movie. It can't do any better than that. So it needs some data. So let me give it some data. So let's suppose that I'll watch a movie, and I like this movie. So what I'll do is I'll drag it across into the green region, which means I'm rating this movie as one that I like. Okay, what's happening is that the other movies, the ones I haven't yet watched, have been arranged on the screen in a particular way. Now, the vertical position is actually irrelevant. They're just spread out vertically so that you can see them. What matters is the horizontal position. What this probabilistic model is doing is assigning a number, a probability, to every movie that I haven't watched, and it's the probability that I will like that movie. So if the movie was positioned down the right-hand side of the white region, that means the system is very, very sure, certain, that I will like the movie. If it's down the left-hand side, it's certain that I will dislike the movie. And if it's in the middle, it's 50-50. So what you see now is that there's a lot of white space down the right and down the left, and most of the movies are in the middle. It's very unsure, for most of these movies, it's very unsure if I'm going to like the movie or not, because all it knows is I liked this one particular movie. So there's a high degree of uncertainty in the system. And not surprisingly, it has very little data. So let me give it a little bit more data. Let's pick another movie. And I'll say that I don't like this movie. What you see happening is the movies are spreading out towards the side. The probabilities are moving towards 0, meaning I definitely won't like it, and 1, I definitely will like it. The system is becoming less uncertain. And this, if you like, is the modern view of machine learning. It's a computer having beliefs in the world that are expressed as probabilities, and when it sees data, it updates those beliefs. Those probabilities change through a computational process. So let me give it a couple more examples. Some movies that there's one I like. Imagine that's one I don't like. So after seeing 4 movies, what you see is that there's now a lot of white space down the middle, and it's now pretty confident that I'm not going to like these movies. It's pretty confident that I will like these movies. So roughly speaking, what's going on is that it's analyzing the patterns of likes and dislikes in the population. It's comparing them with my particular likes and dislikes, and then it's inferring the probability that I will like other movies. I'm just going to use this demo to show you one other thing. I talked about the difference between data and information, and this gives a very beautiful example of that. Let's take a movie down the right-hand side. This is a movie where it's almost certain, it's very, very sure that I'm going to like the movie. So let's suppose that I watch that movie. Here's one down the right-hand side. Let's imagine I watch the movie. Let's suppose I do like this movie, so I'll drag it into the green region. Watch carefully what happens when I let go of the mouse button. Watch what happens to the other movies. I don't know if you saw that. Let's try another one. So here's one that it's pretty confident I'll like it, so I'll let go of the mouse button and see what happens to the other movies. Tiny update, right? They're spreading out to the sides a little bit, but very little change. Let's take another movie. It's very confident I'm going to like this movie, but let's say, no, actually, I didn't like this movie. So I'll drag this across to the red region. Now, watch carefully what happens when I let go of the mouse button. Okay. What's the difference? Well, the difference is now going back to being very confused. Look, there's lots of movies in the middle and white space down the left and down the right. So what happened there? Well, every time I rate a movie, I'm labeling it 0 or 1. I'm giving precisely one bit of data. So in each case, the amount of data is identical. But if it's confident that I like a movie and I say, yes, I do like it, there's very little information in that data. It's unsurprising to the system. If there's a movie that's very confident that I will like, and I say, no, I don't like it, it's very surprising. And there's a huge amount of information. In fact, Claude Shannon, who invented the field of information theory, actually defined information as the degree of surprise. And the information, if I take a movie on the screen somewhere and rate it as a movie that I like, then the information content goes from 0 here, logarithmically to infinity as we go across to the left-hand side. So the amount of information in the data depends on the context. So just because you have terabytes of data, you may or may not have lots of useful information. So let's go back to the presentation. I said that the technology that I was showing you was just a toy demonstration, but exactly the same software powers the recommendation engine that runs on the Microsoft Xbox Live platform. So this is serving hundreds of millions of recommendations a day on games and movies and so on. So what you saw there was an example of personalization. In other words, you saw a system learning about my personal movie recommendations. And just a little aside, I thought I'd mention what I call the paradox of personalization. I think this is quite interesting, and it's something that I think will be increasingly prevalent in the years ahead. Computing will get very personal, be very tuned to our personal interests, our personal activities and preferences and so on. But there's an interesting thing about personalization. Here's an example of personalization. This is handwriting. I just got a whole bunch of different people to write the word uncertainty down. As you can see, there's a lot of variability in the way different people write this. Now, imagine I'm building a system which is going to recognize handwriting. It's going to translate electronic ink into text. Well, one way I could do it is, and this has been done, of course, is to collect data from tens of thousands of people. You get them to write out text, copy out text. You have the ground truth text, and you have the electronic ink. And you can train a machine learning system to take the ink as input and produce that text as output. So you train up your machine learning system. What I have then is a machine learning system that's trained on data for the whole population. So it works fairly well, but it's not yet good enough. I can make it a whole lot better by personalizing it. I can train on your particular style of handwriting, then I can improve the performance enormously. So another approach is to say, I'm sorry, I'd like you to just copy out the complete works of Shakespeare for me, and when we're done, we're going to train the most amazing handwriting recognition system. Okay, I don't think you're going to go for that. Now imagine we do the following. And I'll describe this intuitively, but I want to emphasize there is some deep mathematics behind this. I'm very happy to cover that in the panel session or afterwards if you wish. But let me just give you the intuition. Imagine I collect data on handwriting from tens of thousands of people, and I build a rich probabilistic model of that data. I might discover that there are, say, 153 different styles of handwriting in the English language in the UK, let's say. For each of those 153, I might have data from thousands of people, so I can train up a model for each a machine learning solution for each of those styles of handwriting. Now when a new person comes along, I don't need you to copy out the complete works of Shakespeare, I might just need you to copy out a sentence or two. Because, roughly speaking, to put something into n categories, if they're balanced at least, you only need log n bits of information. So I may only need a few samples of handwriting to say, ha, your style of handwriting is style number 27, and I've got data from 5,000 people already on style 27, so I can ship to you a personalized handwriting recognition system. What we actually do is even better. We do what we call a hierarchical model, which uses the data from everybody to learn about handwriting in general, and then individual data to specialize that to the different substyles. So all of the data actually gets used in the personalization system. I just call it the paradox of personalization because to build a highly personalized system that's tuned to you as an individual, the best thing I can have is data from millions of people. Okay, picture of a red bus. Why have I got a picture of a red bus? This obviously is a talk without mathematics, but the mathematics behind this is very beautiful. It goes back a quarter of a millennium. To people like Laplace and Bayes and so on. And it represents, I think, the next major step in computation. I've already talked about the shift from computation as logic and determinism to computation in terms of uncertainty, making uncertain variables, making probabilities first-class citizens of software. So I'm just going to show you one little property of probabilities, which I hope you'll find interesting, and which may help to illuminate the idea that this is really very different. This is not just about adding a few features to a programming language and off you go. This is really quite fundamental. So we've got a bus, and let's suppose we agree that the bus is longer than the car, and we'll suppose that the car is longer than the bicycle. Okay, then using your expert logical powers, you will deduce that the bus is longer than the bicycle. You all agreed on that, I hope. That's called transitivity, and that's a property of deterministic numbers, numbers about which we are uncertain. But if we now go to random variables, to uncertain quantities, quantities described by probabilities, this no longer need apply. So this is very bizarre. And this is not just a hypothetical thing. This really exists. I've got some in my rucksack here. These are dice, and they are unbiased dice. Each is a cube. They're not weighted in any way. They're equally likely to land on any of the 6 sides. The unusual thing about these dice, though, is just the choice of numbers. So instead of having the numbers 1 to 6, there are the numbers 0 to 6, but they're arranged in interesting ways. So this one actually has a 3 on every face. So every time you roll it, you always get a 3. This one has some 4s and 0s. This one has 2s and 6s. The same number doesn't appear on more than one dice. So if you roll one die against another, one of them will always have the higher number. We'll call that the winner. So let's pick a pair of these. Let's roll the red die against the yellow die. Then sometimes the red die has, I think, 4 2s and 2 6s. So 2/3 of the time it will come up with a 2. This always produces a 3. So 2/3 of the time, this die will generate a bigger number than this one. And 1/3 of the time, the red one will win. So I can take a bet with you. Sorry, I'm always picking on you. I can take a bet with you. We'll do the best. We'll pay for £5. We'll do the best of 11 rolls. And whoever gets the most wins will keep the £10, the other person's fiver. So this die will beat this one. It will generate a bigger number. This will generate a bigger number than this 2/3 of the time. Now, you can see what's coming. This one will generate a bigger number than the yellow one 2/3 of the time. This number, the number rolled by the green die, will be bigger than the number rolled by the purple die 2/3 of the time. So far, so good. But now the really bizarre bit is that the red die will produce a number that's bigger than the number on the green die. Again, 2/3 of the time. These are non-transitive. Each one is bigger than the previous one in the sequence, in the sense that 2/3 of the time it will produce a bigger number. So, you've all got friends who haven't been to this talk, I'm sure. What you do, you purchase a set of dice from me afterwards, and you go and make a bet. You let them inspect the dice. You let them choose whichever one they wish. You pick the next one in the sequence. You do the best of 11. They get fed up with losing. So they say, I want your die. You say, no problem, you have it. And you pick the next one in the sequence, and off you go. So it's a bit of fun, but it's really just to illustrate that probabilities are very, very different things from deterministic numbers. So when we go into the world of uncertainty, we need a new kind of mathematics if we're to do things properly, if we're to do things efficiently. So I'm going to finish with just one last thought, and it's just scratching the surface of something which is a very hot topic in research right now. We're starting to use this industrially, but it's very early days. Most of the problems in this space are unsolved, but it's something which I find enormously exciting. It's called probabilistic programming, and really I should give a 1-hour lecture on this, so I won't have time to explain this in detail. All I can do in one slide is just give you a flavor for this. So if we go back to something like that movie recommender example, it's taking in some data, and it started life, of course, as some code written in C++ or C# or Java, whatever it might be. The code was compiled down to machine code, and then in the processor it was combined with the data, it crunched around, and it output predictions, in this case predictions with uncertainty. Now, producing this software is just like producing any other software. It's thousands of lines of code, lots of scope for mistakes. You have to correct the bugs, you need lots of testing, all the usual issues around software. So this is very complex and needs a lot of skill to produce this, what we call this inference code. If, however, we imagine a programming language in which probabilities are first-class citizens, we'll call that a probabilistic programming language, in which these random variables are built into the language, that opens the possibility of what we call a probabilistic program. And this can be a very, very short program, because essentially what this program describes is not the processes that the computer has to go through to do all the computation. It's a much higher level description. It's what we call a generative model. It's just a description of how the data comes into being. If you like, a little description of the world, the processes by which data comes into being, described by very compact code, a few tens of lines of code. And then a piece of magic happens called a probabilistic program compiler, which generates this code automatically. Now, there are examples of probabilistic programming languages that have been around for 20 years or more. There's one has a wonderful name of Bugs, a great name for software. It's Bayesian inference using Gibbs sampling. It's been widely used in the medical domain, very famous in the medical statistics domain. It uses some computational techniques that are very inefficient, but very general purpose. So it's very general purpose, but it only operates on a small scale. The challenge today is to make this operate at sort of web scale. DARPA last year announced a $50 million research program in probabilistic programming. There's tremendous interest in this worldwide right now. My own research group spends a lot of time working on this. We have a system called info.net, which is our particular take on probabilistic programming. The aspect that we're most interested in is sacrificing a little bit of generality in order to have scaling. So we want to be able to apply this technique to millions or billions of data points. We already have industrial examples that are about to be deployed where this is operating at web scale in real time. So although we have success stories already from probabilistic programming, I'd say we're sort of 5% of the way there. I think in the coming years and over the course of the next decade or so, these techniques will mature, and it will allow people to build rich probabilistic models using a very high-level language, much higher level than a regular computer language, and they won't need to understand all the details of inference algorithms. They won't need all that specialist knowledge. They'll just need their domain-specific expertise, whether it's finance or advertising or whatever it might be. That's the dream of probabilistic programming, to make that fourth level of that data hierarchy accessible to a much broader range of people. Okay, thank you very much.